and SIC measurements in such. Máté, please go ahead.
Thank you, Tomek, for the introduction. I hope you can hear and see me. If not, just shout or something so that I notice. So thank you, Tomek, and also thanks for the organizers. I think now that this is the last day of the conference, we can safely say that it has been a successful event, and it's been as close to an in-person conference as probably possible. And so the organizers did a great job with that. And I also want to thank the program committee for allowing me to present this work here, which, as Tomek said, is about mutual unbiased bases and symmetric informationally complete measurements. I won't really talk about the latter, so if you're a fan of SIC POVMs, then maybe it's a bit of a disappointment, but it's in the paper. And well, this is a collaboration with Arvind Tavakoli, Danil Rosser, Daniela Bankal, and Jędrzej Kaniewski. And this is where you can find the paper. So I think I'm kind of lucky because we've been talking about nonlocality just now and also previously at the conference, but still I would just like to quickly go through what is the setup that I'm interested in, and have new figures so that you get used to my figures. So we will be in the non-local scenario, and whenever I say non-local scenario, I think about two parties, which are usually called Alice and Bob. Two parties having access to some sort of devices that have some classical input and classical output. These classical inputs and outputs are simply they're coming from some discrete set. So Alice can choose between capital X different settings of her box. You can just think of it as having X different buttons on her box, and whenever she presses a button, some kind of answer is provided by the box, which is this lowercase a, which can have capital A different values. And Bob has access to a very similar device, on which he just pushes buttons and sees some sort of answers. And the key assumption here is that the events of pushing buttons and seeing answers is space-like separated, which can be sort of motivated by special relativity, and that we are not allowing any communication between the parties. So they, Alice and Bob, are in some sort of distant labs, pushing buttons and registering their outcomes, doing this many, many times to kind of try to characterize what these black boxes are doing. And once they've done it many, many times, they can meet and see what they got. And the quantity that characterizes this experiment is what we call the correlation, which is simply the probabilities of obtaining an outcome A for Alice and an outcome B for Bob, given that they've chosen the settings X and Y. So this is what essentially describes this whole experiment. And we can just collect these numbers, and sometimes it's kind of convenient to just collect them in a big vector, in a real vector space. You can always embed it in this R to the X, Y, A, B. You can also embed it in a smaller space, but it doesn't really matter now. The important thing is that you can just write this as a vector with all these numbers, these are probabilities. So this is the scenario, and now we're going to put some models behind it. How can we explain such a correlation? And the first thing is the so-called local hidden variable models, which in the non-locality scenario, this is what people call classical, basically. So what we're imagining here is the way that these answers are provided by the boxes is via some hidden variable, which is called lambda here. So there is some sort of common cause for these answers apart from the settings that the parties choose. So if you're imagining your Alice, you get this lambda from somewhere. This is some input to your box that you're not seeing or don't have direct access to. And based on this lambda and the settings that you've chosen, there is a deterministic function, fa, that provides you A, which is just, if I know X and I know lambda, I know exactly what A will be. And the similar thing happens on the box side. And the fact that we're not having access to this lambda is reflected by the correlations emerging as some sort of convex combination over different possible values of this lambda. So this is why it's called hidden variable, because what we see is only the xa and the yb. So if we want to describe the correlations, we have to just average over this hidden variable that we don't know. So then eventually the correlations that we see are a probabilistic mixture of local deterministic events. So deterministic refers to the deterministic nature of these functions, and local refers to the fact that Alice's outcome doesn't depend on what Bob did, and vice versa. And then you probably know that in order to describe a local hidden variable model, you don't need to assume that these are deterministic functions, but you can also incorporate events when locally there is some randomness here as well, like Bob flips a coin or something. But these can essentially be absorbed in these probabilities here. So I will only give you this this description, but these models are equivalent. So this is the sort of classical model, and now we're moving on to the quantum model, in which case this shared common cause is a quantum state, this rho. So the parties get a bipartite quantum state, and the way they extract some classical information from the quantum state is probably obviously a measurement. So I will describe measurements by positive operator valued measures, POVMs. So we have a tensor product Hilbert space, HA tensor HB. We have some measurements on both, and the quantum state lives on this tensor product Hilbert space, and the correlations can be written via the Born rule, essentially. So this is the quantum model behind these non-local experiments. And what we see once we compare the classical and quantum models is that if we kind of try to plot these, what are the achievable regions, what are the achievable correlations, what we find, well, first the local hidden variable models form a polytope, I call this L, and the quantum correlations also form a convex set, but they are strictly larger. There are some correlations that have a quantum explanation, but they don't have a local hidden variable model. And the kind of standard way to detect when something has a quantum realization but not a local hidden variable model is via Bell inequalities. So this is kind of a drawing example. I have these sets. If I have a linear functional on my probabilities, on my correlation, like remember that we can just embed these probabilities in some real vector space. So I can write a linear combination of my probabilities, and like here you see that all local hidden variable models should be sort of on the upper part of this hyperplane. So whenever there's such an inequality that is satisfied by all local hidden variable models, but there are some quantum correlations that violate this inequality, then we call this a Bell inequality. And this is what you can use to detect non-locality, when by non-locality we mean Bell non-locality, which means that the correlations do not have a local hidden variable model. And so this is kind of foundationally already very interesting, and it already has a few applications if you wish. And I will be interested in device-independent quantum information processing. So now we take this kind of Alice and Bob experiment and we embed it in a tripartite case. So we imagine that Alice and Bob are trying to achieve some sort of information processing task. We will be interested in random number generation or key distribution, but they don't want to assume anything about the state that they have, anything about the measurement that they have. So it's really like this sort of black box scenario, but only based on the correlation that they observe. They want to kind of deduce something about the workings of their devices in order to use this for, let's say, random number generation. And the assumptions that usually go into these device-independent protocols is that there is some third party that they don't really have access to, which is usually referred to as Eve, as like the eavesdropper. And what happens in reality is that the state is not a bipartite state, but it's a tripartite state shared between Alice, Bob, and Eve. And Eve is also like allowed to make some sort of measurement and get some classical outcome. And then the correlation, the full correlation, is a tripartite correlation. But Alice and Bob only have access to the bipartite one, which is like You can get it from like summing over the outcomes of Eve. So they only have access to this black thing, but in sort of the background we have an eavesdropper, and the tasks that we can do. First one is random number generation, where let's say you want to infer just by looking at the bipartite correlations that the outcome of, let's say, Alice is independent of any potential eavesdropper that fits in this model. This is, sometimes you actually can deduce such a claim just by having access to the bipartite correlations. And this is what's called device-independent random number generation, because you don't really have to assume anything of your devices, just that this description is valid, which is essentially saying that quantum theory is valid in this formulation. So the one task is random number generation, and then there's another one which is, if you wish, a slightly stronger requirement, which is key distribution, which is similarly, we want that Alice's outcome is independent of any eavesdropper, and also is correlated to Bob. So Alice and Bob are trying to establish some key which is private to them. So they want to have like exactly the same outcomes, but in a way that nobody else can know what this outcome is, which is then very useful for cryptographic protocols. So these are kind of maybe the two most well-known device-independent quantum information processing tasks. And the important thing to notice is that it is necessary in order to achieve these tasks to violate the Bell inequality, which is kind of easy to see from this kind of picture. If we don't violate the Bell inequality, there's a hidden variable model, and then this hidden variable is also accessible to the eavesdropper. We know that these are just some kind of deterministic functions. So, well, essentially the eavesdropper always knows everything. Everything is deterministic, so you will not be able to generate any random numbers or generate the key. So Bell inequality violation, Bell nonlocality allows, in principle, to obtain device-independent random numbers and device-independent keys. So this is what I wanted to tell you about Bell nonlocality, and now I'm trying to tell you about mutually unbiased bases in Bell experiments. So for this, first we should see what mutually unbiased bases are. So for now it's a bit just abstract and mathematical, but essentially mutually unbiased bases are a pair of orthonormal bases on some d-dimensional complex Hilbert space. So I call them P and Q. So it's just d orthonormal vectors, such that if I take any vector from the basis P and I compute the overlap modulus square with any vector from the basis Q, I get the same number, which is 1 over d. This 1 over d is just a consequence of the normalization. The important thing is that any two of these vectors have a uniform overlap. So this is sort of the mathematical description of mutually unbiased bases. And an example in any dimension is just the eigenbasis of the generalized Pauli operators. If you don't know what they are, then you probably do know the two-dimensional case is just the Pauli Z and X matrices and their eigenbases. So like the computational basis, the 0, 1 basis, and the plus minus bases. These are mutually unbiased bases in dimension 2, but they do exist in every dimension, and you can construct them in this way. And well, these are so far just some kind of bases, but we're interested in quantum measurements corresponding to bases. So whenever you have a basis, you can just construct the rank 1 projective measurement projecting onto these one-dimensional spaces spanned by the basis elements. So these are kind of the measurements we will be interested in. And when I say mutually unbiased bases or MUBs, I often just think about these kind of projective measurements. And they have like many uses in quantum information, most likely because of like the nice symmetric properties, and really they appear in a lot of tasks. But what I will be interested in today is MUBs in Bell experiments. And I put here state of the art, but okay, there's also a little asterisk. So it's not, I won't tell you everything about MUBs in Bell experiments. I will basically just tell you about the two-dimensional case and maybe the most well-known Bell inequality, the CHSH inequality, in which case the inputs and outputs are bits everywhere for Alice and Bob, And now I denoted Bob's measurements by P and Q just to have maybe a bit simpler notation, because I just have two measurements. So you might imagine that these P and Q will actually be the MUBs eventually. So here is the CHSH inequality. Again, we just want to infer something about the states and the measurements only based on the observed correlations, which can be written like this via the Born rule. So here I put in PB or QB depending on what is the setting for Bob. And well, okay, I can write down this is the CHSH inequality. This is just some linear combination of the observed probabilities. And we know this is a zero-sum bound, that if you assume that quantum theory is correct, so if you want to write your correlations in this form, the maximum value you can achieve is 2 times root 2. And the interesting thing is, for now, is that whenever you see the maximal value, exactly the maximal value, you can actually say a lot of things about your measurements. You can say that Bob's measurements, let's say Bob's measurements, but similar things apply to Alice. Bob's measurements are projective, and they satisfy this kind of anti-commutation relation. And this, in fact, implies that Bob's measurements must be mutually unbiased spaces up to some extra degrees of freedom and the local unitary. So note that we did not constrain the dimension of the Hilbert space. So we cannot say kind of what is the maximum dimension that these things act on, but still we can certify that the measurements that they have are some qubit MUBs, and maybe there is some extra degrees of freedom where nothing happens, and the measurements are equivalent on this qubit space up to a unitary. And this is called self-testing, basically because you only need to look at the correlations, and you can say a lot of things about your measurements. Essentially, you can characterize them up to whatever is like reasonable in a bare non-local scenario. So I just write it out with some formulas. Maybe this is not very enlightening, but so this is what I mean. Like I can say that Bob's first measurement is the 0011 measurement up to like some unitary, and this identity, this trivial space here, and the second measurement is the plus minus. So this is kind of they have a two-dimensional MUB configuration. And also, actually, you can also self-test the state. You can also say that the state must be essentially the maximally entangled 2-qubit state, this phi plus. So that's great. And now we can use this actually for device-independent quantum information processing. So now, again, I have this black box scenario, but now I assume that I saw the maximal CHSH violation. This allows me to basically characterize my state and my measurements just from the observed correlations. And so now I see that I can actually use this for device-independent random number generation, because I have this state and I measure, let's say, Bob measures sometimes in the 0-1 basis, but in backhand basis will give a completely random outcome, which nobody can predict a priori. So this is how I get random numbers from this. And I can also use it for quantum key distribution. I add another setting for Alice for this, which is exactly the same as one of the settings of Bob. And now these measurements will give me random outputs, which will be exactly correlated, you see, because I measure the maximally entangled state. Whenever Alice gets 0, Bob gets 0. Whenever Alice gets 1, Bob gets 1. But nobody can predict a priori which outcome they will get. So this is how you can use this self-testing result. And what we're interested in now is higher dimensions. So this is dimension 2. But in higher dimensions, I can actually get potentially more random bits because my outcome is not binary, but it has t different values. For this, we need a device-independent characterization of MUBs in higher dimensions, which should be an analog of these kind of algebraic definition. So we need an algebraic characterization of high-dimensional MUBs such that we are not referring to the Hilbert space dimension, and still we somehow want to capture some essential properties of MUBs that make them useful in these kind of device-independent scenarios. So what is the property that we want to certify? This is what's known as complementarity. So now I will give you just an equivalent definition of MUBs, which captures this complementarity property. So I will define MUBs as two projective measurements in a d-dimensional Hilbert space, such that if I have a state, which is an eigenstate of one of them with eigenvalue 1, then the other measurement on this state will give me a completely uniform random outcome, and the other way around. So you can maybe easily convince yourself that this is exactly the definition of MUBs. And the problem with this is that it's not device independent, because it explicitly refers to the Hilbert space dimension. So now we make this device independent. So I just put on the definition again. So you remember this is exactly the MUB definition, just formulated in a different way, in a bit more operational way. So the problem was that we had this dimension here. So then what we do is very simple. We just remove this from the definition and call the resulting measurement mutually unbiased measurement. So we have an M here. And now we don't assume the Hilbert space dimension, but the definition is that I have two projective measurements. If I have a state with, on which one of the measurements give a definite outcome, then the other measurement will give me a completely uniform outcome. So this is like an operational characterization. And we also prove an equivalent algebraic characterization. So now I just have two POVMs, and in terms of the POVM elements, I can characterize exactly these kind of measurements. So we have a nice algebraic characterization of this operational definition now. And this is device independent because I don't restrict the dimension of the Hilbert space, just the number of the outcomes. And also, if I take rank 1 projective measurements, this will actually recover the MUB definition for me. So, well, on this slide, I will just argue that this is the right device-independent notion of mutual unbiasedness. So actually, if we take these measurements, we get measurements which have very similar properties to those of MUBs. So if you know about this, fine. If you don't, just believe me that this is good. So if you write some entropic uncertainties, which is kind of quantifies how much randomness you can get out of your measurements on any state, we get exactly the same relations for MUMs as we got for MUBs. Also, if we look at how incompatible a pair of MUMs is, we get exactly the same values as we would get for MUBs. So they have very similar properties to MUBs, but they are a device-independent notion. And if I take dimension 2 and 3, actually MUMs are basically the same as MUBs in the sense that they are a direct sum of d-dimensional MUBs. So maybe I have many copies of MUBs, but I can identify sort of d-dimensional spaces on which my measurements act as d-dimensional MUBs. So if I take d equals 2, then it's exactly the same thing. The MUM definition is exactly the same thing that I can certify in the CHSH scenario. So these are the similarities, but then they are not exactly the same notion of MUBs. And the way we kind of prove this is that in dimensions, well, for outcome numbers 4, 5, and 6, we find explicit examples of MUM pairs of mutually unbiased measurements that are not direct sums of d-dimensional MUBs, and they cannot even be mapped to MUBs with any completely positive unital map. So they are like a strictly more general notion. And also, maybe if you're interested in the MUB problem, I can tell you that there are an unbounded number of MUMs for any outcome number d, but this also needs an unbounded dimension. Right, so now we have this notion of mutually unbiased measurements, and what we do in this paper is that we give a device-independent certification of these mutually unbiased measurements. So again, we have a bad scenario. Now it's a bit more complicated than the CHSH, but notice again that on one side we just have two measurements. So these will be the two measurements that we are trying to certify that they are mutually unbiased. They need to have d outcomes. And then, well, on the other side, we have slightly more measurements, and it's a bit more complicated. But again, what we want is based on these correlations, we want to deduce that what we have in this box of Bob are mutually unbiased measurements. So we have a bell functional. I won't tell you the details of this functional, but we know what is the maximal value you can reach in quantum theory. And whenever you do see this, this maximal value, this allows you to certify exactly these relations between Bob's measurements, which is exactly the algebraic conditions for mutually unbiased measurements. And so this is how you certify MUMs. And this also gives us, well, as far as we know, this is the first example of a correlation. So like a correlation in the space of all quantum correlations, which is an extremal point. But this is not a self-test. It doesn't self-test the measurements in the sense that there are MUM pairs that are not equivalent up to a unitary. Even for MUBs, these exist. I can find a pair PQ and P prime Q prime, which are mutually unbiased bases, but they are not related by unitary. So I get an extremal point, but I cannot characterize my measurements up to a unitary and some extra degrees of freedom. And an additional thing, what we do is we do actually self-test the state, and we get the maximally entangled state in dimension D. And this then allows us to use this first scenario for device-independent key distribution by adding another setting for Alice. So here, like, because I know the state, it's a maximally entangled state. Actually, one of the measurements of Bob can be just a measurement in the computational basis, and then I add the same basis for Alice. So these will give me completely correlated and completely random outcomes on the maximally entangled state, which certifies log2d bits of the Hill key, which is the maximum you can get from a d-dimensional system. So this is how we can use our construction for high-rate device-independent quantum key distribution. Right, so I will sum up what I said. So basically, we introduced a device-independent notion of mutual unbiasedness, and we found a class of measurements that have very similar properties to those of MUBs, and it's a device-independent notion. But it's a strictly more general concept because we didn't have that all of them are direct sums of MUBs. And then we provide a device-independent certification of these classes of measurements. And it's the first example, which is an extremal point of the set of quantum correlations, but it's not a self-test. And we use this for device-independent quantum key distribution. And further things that we have in the paper is a very similar program for CPOVMs. So we have a device-independent notion of symmetric informationally complete projections. We have a device-independent certification of these measurements, and we can use this device-independent certification for device-independent random number generation. So look at the paper if you're interested in CPOVMs. And thank you for your attention.
Thank you very much for this super clear talk.